Yeats. And so let's welcome Karen Yeats, who will be telling us about the fixing graph theory Feynman periods.
Hi. So thanks for inviting me, and thanks for coming to listen. I was asked to do a little bit of a review of these Feynman periods, or what people are calling sometimes Feynman periods. So at the very end, I'll say something small that's new and that I'm involved in, but mostly I won't. Okay, so what is it? I'm a mathematician first, so I think I'm going to define something. And here's what I'm going to define. So I want a graph G, because it's that kind of a talk where the first thing you have is a graph. And what do I want to do with this graph? Well, I'd like to sum over all the spanning trees. And then what do I want to do? I want to take the monomial of the edges that you have to cut in order to get that tree. So you have a variable AE for each edge E of the graph G. Okay, and so depending on where you come from, you might call this a Kirchhoff polynomial or a dual Kirchhoff polynomial, or you might call it the first semantic polynomial. But in any case, it's a nice polynomial. And then you might want to write down an integral that uses it. And I sort of want to morally think of it as this integral. But of course, you wouldn't do well in your calculus class for writing down that integral. So I better actually change it a little bit. So let's just integrate over all the variables except for one. And that last one we'll set to 1. So just this guy. This is all we're talking about. So at some level, I don't have to say anymore, because we're going to, that's this period, and that's what we want to compute. And everything else, I'm actually not going to compute anything, because you guys are much better at computing integrals than I am. But what I'm going to do, you might have noticed my affiliation is with the Department of Combinatorics and Optimization, is I'm going to do some combinatorics that tells us some things anyway about this period. And I'm going to overview some of the things that people know about how the combinatorics of the graph tells you something about this period. Okay, it's worth pointing out that it's manifestly written in an appropriate way to be a period in the sense of Kutsevich and Zage, because we're integrating something algebraic over something polynomial, and everything is happily rational, polynomial, algebraic as appropriate. There's a lot of freedom to shift between those things. And these are things that you may have been hearing about for some time. I just wanted to do some examples. So just for people who haven't been playing this game before, we ought to start at the beginning and do some examples. So let's just make a Kirchhoff polynomial. We'll do this graph, because there's only so many graphs you can do by hand in a talk without driving everybody crazy. So if I let the edges be A, B, C, and D, I want to sum over the spanning trees. So what are the spanning trees? So AB, for instance, is a spanning tree, which means I put the things that were not the spanning tree in there. AC is also a spanning tree, so I put the BD in there. AD is also a spanning tree, so I put the BC in there. Somehow this isn't the best format for you guys telling me the answer, which is what I would usually do. So I think I would just write the last few terms. You're going to also get the AC and the AD. Okay, and so then you got to integrate that. Well, maybe you're not too happy about integrating that guy because it's got a subdivergence, so it won't converge. But if you do integrate something that does converge, for instance, you might want to take this little guy. That's the first one. And that one sort of famously gives you a 6 Riemann zeta of 3. Okay, so that's the thing that we are talking about. Okay, why are we talking about this thing? Well, or you might say, okay, it's actually really time to go have a coffee or something. For me, it's almost time for lunch. So, because in fact, we already know these things, right? They're part of the story of Feynman integrals. And why are they part of the story? Because, well, you can go look in some textbook that you like that does some Feynman integral calculation. And sure enough, you will see, look, what are these things? They're just your residue. So they're the one part that's always going to be there, no matter what more sophisticated way you use to compute your Feynman integrals, no matter what extra stuff is going on. They're always just sitting there as the residue, independent of your normalization scheme and all these sorts of things. And lots of people have been computing these. And I would particularly note David Broadhurst, who's, I think, still here in the audience, calculated quite a few of them in the 90s in particular. Because it's just this residue, it's in your contribution to your beta function. But of course, these are quite simplified. All the parameters, all the physical parameters are gone. And so higher legs are not going to be interesting. More masses is not going to be interesting. And so higher loops is what is interesting. So this is a loops game. It's worth pointing out that I wrote the parametric form because that's sort of the nicest one from a pure mathematical perspective, perhaps. But of course, it's just this residue of the Feynman integral. So you can write it in any of the ways you're used to writing a Feynman integral. Let me just write some down for you, just so you see what I mean. I mean, what can we do? Well, we already wrote the one that was supposed to look like this, right? And I said, oh, it's morally just that. And then I said, well, okay, but it's not really that. And I set one of them to 1. But if you were an algebraic geometer at heart, you probably didn't actually like that, because you'd probably rather think about it as a projective integral. So you the same thing, but let's not set that. But we want to now work over some projective form. And the same holds in other cases. So, maybe I would like to write this thing in momentum space. So then what am I really doing? I've got some product over the edges of the graph. And what do they each have? Well, they each have some momentum of the edge. And then I better square it. And then, okay, that's pretty good. And then I could write that affinely, or I could write it projectively. Let's write it projectively first. I guess this is a slightly different. This is like the P version. This would be sort of the A version. And then what would I have to do here? Well, I'd better set one of them to 1. So P1 to a unit vector 1, a bold one, this bold one, and integrate the rest of them. Subject to my delta functions. Oh, I didn't leave space. Did not leave space. Okay. In fact, let's just not do it that way. There wasn't really space there. Let's not do it that way. Let's do your standard little game. Let's put this back, and then we can just do one for each. We can take a basis of the cycles, so the loops. So then, well, I don't really want to write it all down, but anyway, you know what I want to do. I want to sum over the loop. So I want my PEs to be the sum of the cycles that go through the edge, plus or minus P of the cycle, I should say loop, and then go from there. Okay, so that's fine. And I can also do it in position space, and it's all exactly the same. And in both cases, I can do it in an affine way or not in an affine way, right? So now I'm going to take a product and take an x1 xi minus an xj, and you know exactly what I want to do. And I could do it in a nice projective way, like this. And I could do it in a nice affine way. And I'm going to stop doing this pretty soon because I don't. So I better now set some things. Something like that, and then. Okay, fine. You write it whatever way you like. Okay, but why should you care? Because, you know, you already have much more sophisticated ways to think about Feynman integrals. So why should you care? Well, as a physicist, it is a part of what you need, no matter what more sophisticated things you're going to do later. It's relatively computable. And I would argue that pretty well any simplification that you can find that's still got some richness to it, but certainly this one seems to postpone, not remove the interest in complexity, while still making the structure clearer. So I think they're actually very interesting things to study. Now, if I'm going to speak as a mathematician, which is the way I like to speak, I would say what's interesting about this is that it simultaneously looks like algebraic geometry and algebraic graph theory, which are two very nice things. And even more than that, it asks interesting questions that from a pure math perspective, maybe you wouldn't necessarily want to ask. And now that's a general theme, and we've seen that before. We saw that just before in the previous talk, that there are some really nice structures, regardless of how you're thinking about these, that you might want to ask as a physicist. But I'm not so much going to be asking the geometric or looking at the geometric or analytic side of the mathematics. I'm going to focus more on the graph theoretic side of the mathematics. Okay. But of course, you also already know this. This whole talk's about things you already know. No, it's not true. There's some things I think you don't already know later. I'm sure there's one thing at the end you don't know. Because right since Feynman diagrams began, you use the graph structure to try to help you find the best way to integrate a given graph or find connections between integrals or things like that. And we've already seen examples of that, and you guys know other examples of that. The Feynman periods in particular are good for computing edge by edge. And there's techniques for doing that. And here's a few of them. You can use these graphical functions of Euler-Schnitt. So you can use hyperlogarithms, which is closer and related to many of the techniques that we've heard about here. Okay. But now I want to say something concrete about graph structure. I don't want to just say blah, 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 right? There's some graph structure. Of course, there's some graph structure. So what are some specific examples of some of the graph structure? And so I'm going to talk about some of the period invariant graph operations. So things you can do to a graph that don't change this Feynman period or graph period. And the first one we want to talk about is completion. So what is completion? You have to imagine you have some diagram, and you could think of it as a scalar 4-point diagram, right? So there's some sort of diagram that's got 4 external edges. And now let's just add a vertex at infinity and connect it to every guy. Okay, that's nice. So I have some sort of vacuum graph now. But then we'll just remove some other vertex. So I'll pick some other vertex in here and I'll remove it. All right. So adding the infinity was the completion, and removing this other guy was the decompletion. And if you think about what's going on in position space, you might be able to see why I'm calling it that. Because sure enough, you're in position space and you can move around where your vertices are. And what kind of freedom do you have? Well, you have a freedom of what you put to infinity, since you can do these affine transformations to your integral. Okay, now these two graphs, they can easily be non-isomorphic graphs. So let's just do a quick example where we're going to get some non-isomorphic graphs. And again, people who've seen all these stories before, I'm sorry that I'm not saying anything that you don't already know and haven't already seen before. So there is a reasonable graph. Let's just use the color to help illustrate. So I'm going to complete it here. And now let's just pick another place to decomplete it. Now, I want to pick some place where I'm going to get something different going on. Let's see what we can do. Let's try picking here and see what happens. So if I pick here, that means I'll get rid of this. This is going to go away, and this is going to go away. This is going to go away, and this is going to go away. And so what are we going to be left with? Well, and there's still this guy. So there's actually this triple triangle. There's this edge with 3 triangles coming off it. And now there's another vertex that goes to all 3 of them. And then you're good. So, yeah, these guys are external. Okay, so those are non-isomorphic as graphs, as you would expect. because they're related by completion. Now that's a fairly silly example. If you're thinking now about the actual period, if you've played this game before, you'll know this is a 6 out of 3 fellow here, because it's 2 examples of K4 glued together. And there's many more complicated guys. All right, the next period invariant graph operation is also something that as a physicist you've known for a very long time, because of course we have Fourier transform. And you can use, I mean, what do you do with Fourier transform, right? You just walk into some room full of your people who do quantum field theory, and you say, what are you going to do with your Fourier transform? And what you're going to do, you're going to go between position and momentum space, because that's what Fourier transforms do. But of course, in 4 dimensions, it's kind of nice because you can just reinterpret your position space as the momentum space of another graph, or vice versa. And then what is that on graphs? That's the planar dual of graphs. Because what have you done? You've taken what used to be cycles in the graph, i.e. loops in the sense of quantum field theory. And those are now turning into cuts, right? And the things that used to be, well, you might say, well, what is a cut? I guess I need to say a little bit more. What are the cuts? How should I understand the cuts? Well, if you have a cut in a graph, what is that? That's a set of edges that are momentum conserving. So you have this duality between these cuts, these momentum conserving things, and the cycles. And that is exactly your Fourier transform symmetry or your planar dual. Okay, so that's great. I would just note more generally that you don't actually have to stick to graphs, because of course, you know, you can take a Fourier transform even if the graph was not planar, because you have position and momentum space regardless of planarity. In fact, I think broadly speaking, planarity is a red herring in a lot of this. But then what happens? You don't actually get a graph, you get something else. So this whole story works for regular matroids. What's a regular matroid? Well, some of the regular matroids are the ones that are graphs. Those are called graphic matroids. Some of them are explicitly the ones that are duals, so cographs. Those are the duals of graphs. And then there's a little bit more. And a bit more is a special guy called R10. And I'm not going to say anything else about R10 today, so that's fine. And then you just get to glue these things together in a way that should not seem too surprising from a physics perspective. You basically have something there. I've drawn it as if it's a graph. And maybe it's got a triangle here. And maybe you got something else and it's got a triangle here. But now you join the 2 triangles together and you remove them. So I can remove them. That's okay. Oh, erase, erase. Oops, erase too much. Just erase just that guy. And then you join them up. And now drawing it that way, it's not clear that that makes any sense on a matroid, but in fact it does. And you can write down what it means and you do that. It's called a 3 join. We'll come back to 3 joins in a sec. Now, if you want to operationally work with these guys, you actually find you'll do exactly what you would have done before. So if you think about your Laplacian matrix, well, nobody said it had to be a graph, really. And maybe a better way to see it is to think about your incidence matrix or your signed incidence matrix. And that's the one that you usually write this way. And it's got edges along the top, and it's got vertices along this way. And you could write down a matrix like that, but not every matrix is necessarily interpretable as the incidence matrix or the sign incidence matrix of some graph. But as long as it's totally unimodular, so all the subdeterminants are 0, 1, or -1, then it's going to give you a regular matroid. And that gives you enough space to take all the duals you could possibly want. All right, so that's not so much to the point, but it explains at a mathematical level why you're actually just fine doing your Fourier symmetry, even outside of the world of planarity, and you should be. Because really this should all be a matroidal story. Okay. You're like, I don't care. What are some other period invariant graph operations? Here's another one. So at this point, to state it more nicely, we should work at the level of the completed graph. And that wasn't the case the previous time, right? Because that extra vertex at infinity and those extra edges going to it, right? You don't want them there in your Fourier transform. So this is but so the planar duality you don't want to do at the level of the completed graph, but you do here. And then this is a really nice one to draw. It looks like this. So here's your graph. There are 4 vertices here. And now what do? You keep one side the same, and you make the other side look like this. Okay, and it takes a little practice to draw that, but anyway. And now these periods are the same. Well, these are the completed guys. So you have to decomplete, and then the periods are the same. And you kind of prove that in a similar way to how you would prove the completion, right? We said, how do you do the completion? You work in position space and you say, well, actually, I've got these affine transformations, and so I can just put whatever vertex I like at infinity. Poof, done. Well, this one's a little trickier, but it's a similar sort of idea. You put the 4 vertices. You got a freedom to put 4 vertices in a good place. You put them in a good place, and then you have to do a transformation on the one side, but not on the other side. Okay, there's something else that's related to that guy. So what else could you possibly do? Well, let's suppose you're again in that same situation. Okay. Now, we said we're free to put the infinity vertex wherever you like. So let's put it here. So then that guy's not really there anymore. Okay, so now we're really more looking at something that looks like this, and there's just some external edges hanging around, maybe like this. Okay, but now let's suppose one of the sides was planar. So let's take this side and let's do a planar dual. So we'll put a vertex here, put a vertex here, put a vertex here, and then there'll be whatever inside, and we'll do our planar dual. Okay, well, that's kind of nice because we got this side, which has 3 vertices that are special. And we got that other red messy side that's got 3 vertices that are special. So let's just join them back up. And how are we going to do that? Well, look, this guy is in a sort of clearly definable sense opposite to this guy. And so that's where it's going to go. So if I just labeled these guys briefly, A, B, C, then A is the one that ends up here. B, it's opposite to this guy. So B ends up down here. C was opposite to this top guy. So C ends up here. And then we have the red guy on this side. Okay. And now I just have to put infinity back. So put my new infinity, and I have unique places to connect it. Okay, so that's nice. And there's details, lots of details that you want to check, but it works out. What are some other nice graph symmetries? Well, here's another one you might. We already said what a 3 join was. Notice it doesn't say that it's a period preserving thing. The periods are not now equal, but you'll know what the periods are. This is another one that you guys already know, I think, if you play with a lot of these integrals. So say you have that. Okay, well, might as well make that be infinity. So really what I'm looking at is this. Okay, and now you're like, yeah, okay, I see what's going on here. The period of this guy is equal to the period of half of it, with just an edge there, times the period of the other half of it, with an edge there. So that's nice. You get some nice product property. And so you might as well think of these as reducible in some sense, and you don't care about them. And so you really only care when there are no small vertex cuts like this. Okay, it's nice. Okay, well, this last one is not telling you the period directly, but it's telling you something about the period. I actually really like this one, even though it's kind of old now. I'm mostly telling you old things. So what is it? Double triangle. So let's say you got a triangle in your graph. Okay. Let's say it connects to another triangle that they share an edge. So here's two triangles, they share an edge. And now there's some more graph. And I don't even care if it's four regular, but we've mostly been talking about things where it might be. Okay, so there's some more graph. Now what do? You take this middle edge and contract it. Okay, so I contracted that middle edge. What would I do if I contracted that middle edge? I'd get something that looks like this. And this goes like that. And the same rest of the graph is out there. Okay, but I'm not done yet. That's not what I want. I don't like that. That looks yucky. It's not for regular anyway. I don't like that. So first of all, I don't really need those doubled guys. Just one is enough. And now these guys are lacking in something. So I'm just going to put a new edge between them. So it looks like that. Depending how you draw it, it can almost look kind of stupid because drawn like this, I've basically taken a crossing in the drawing of the graph and put a vertex there. But it's not an arbitrary case of turning a crossing into a vertex. It's a very specific one where there's this triangle turning into this pair of triangles. Now that's not a period preserving property, but it does appear to preserve, well, I said transcendental co-weight. What the heck do I mean by that? What's the co? So we've heard about transcendental weight, and in a sort of operational sense, you know what the transcendental weight should be for all of the kinds of functions and numbers you're playing with for doing your Feynman integral calculations, even though the general mathematical question is a much more subtle, but operationally we're fine. We've got it for what we need. Well, that's not even quite true, as some of you know, but close. What do I mean by the co-weight? Well, as you would expect, the numbers, of course, get more complicated as the graph gets bigger, of course, right? You all know that. So by the co-weight, I just mean the difference between the maximum transcendental weight given the loop order of the graph and the actual transcendental weight of the number that you're looking at. And this graph reduction preserves that co-weight. Notice it doesn't preserve the size of the graph, right? The graph has gotten smaller. The number of loops has gone down by 1, but this co-weight is preserved. And I say appears to be, but that's because there are, you know, there's difficulties in sort of figuring out the right way to, well, the point is you can write a precise theorem. It's not just an empirical observation. You can make some precise theorems, but the precise theorems don't quite say that. Of course they can't. They say things about when denominators are 0 and things like that. Of particular interest is this question about the structure of all graphs that reduce to K5. I'd say a little bit more about that in a few minutes. But yeah, I think this aspect of it is very pretty. There's, you've got these Feynman periods, which are a piece of the Feynman integral, and an interesting number theoretically interesting piece, algebraic geometrically interesting piece, also algebraic graph theoretically interesting piece. And here are some nice graph operations that satisfy these things. Okay, I'm going to now move to a related but slightly different topic. So this is a good opportunity to ask if there's any questions now before I move to the next part. All right, the void has no questions.
Yes, I don't see his hands, so I think you can keep going.
Okay, so now I'm going to say something a little bit more specific that I think is very interesting. And it's something that you might have heard me or some other people like Francis Brown or Ulrich Schnetz talk about, which is got called the C2 invariant. So you got to remember your first semantic polynomial or Kirchhoff polynomial. And what do you want to do with it? Well, you have to remember one of the things you could do is put on your algebraic geometry hat. And if you're going to put on your algebraic geometry hat, I once had a PhD student who liked this language of putting on hats. And at one point he was giving a talk and he had found a literal hat somewhere that he decided it was his physicist hat. So he'd take it on and off depending on whether he was speaking as a mathematician or a physicist in the talk. Anyway, I don't have one of those. So what am I going to do? I'm putting on my algebraic geometry hat. And then one of the things I might want to do as an algebraic geometer is I might say, aha, I have an algebraic variety defined by the vanishing of this thing. I'm going to count points on it over finite fields. And so that's what we're going to do. So this here is going to be my notation for the counting points over the finite field of P elements. And if you have played this game before, right, we really are saying FQ or FP rational points on this variety. If you have not played this game before, at an operational level, this is a very simple thing. You just say, modulo P, I have P numbers. I'm going to plug them all in for the variables and see how many times I get 0 modulo P. That's all you're doing. And so in particular, notice it's an affine kind of point count. Okay, then it turns out that as long as the graph has at least 3 vertices, you can always, this is always a number that's divisible by P squared, and then we're going to take that guy mod P, and that's the C2 invariant. This is the thing you want to compute. And so notice that for a given graph, what is C2 really? It's really a sequence, right? There's the C2 at 2 of the graph, sorry, the C2 at 3 of the graph, etc., the C2, 5 of the graph. So you think of it as a sequence indexed by primes. You could even put in some prime powers, although we usually don't. So I'm going to just put in a little, you could do a 2 squared. Or you could not. You could stick with the primes. Some of the techniques only work for primes. So. Okay, so this is the thing. All right. Why? Why do you want to study this thing? This seems like a bizarre thing. Again, if you haven't heard this story before. So why do you want to study this thing? Well, this is a little bit of a history story, which again, I know some of you know. So what happened here? People like David Broadhurst and Dirk Kreimer had computed a bunch of these Feynman periods. Not calling them that yet, but computing them because they're nice, useful things to compute in the 90s. And at the time, it looked like they might all be multiple zeta values. At the time, the ones they had recognized then were all multiple zeta values. And it was a plausible conjecture at that time that maybe really everything was going to be multiple zeta values. Maybe by restricting to this period, maybe unlike what I said in an early slide, where the complexities you see in the full quantum field theory are just postponed, maybe it's really simpler and it's just multiple zeta values. Well, it turned out that was false. Many of you know this story. And I mean, it wouldn't be much use for elliptics and beyond if it was only multiple zeta values. But along the way, something very interesting happened because you say, okay, well, if it were all multiple zeta value, it shouldn't just be because of some stupid coincidence. It should be for some good mathematical reason. Okay. Kontsevich said this, right? Should be some good mathematical reason. What is the good mathematical reason? The good mathematical reason is that the underlying motives in the sense of algebraic geometry should be mixtate. That's the correct good mathematical reason if what you're seeing is all multiple zeta values. Okay. But in that case, now notice, this is a fact about the geometry of the variety of the Kirchhoff polynomial, right? You're taking an integral over it, you care about the behavior of that integral. So we said already it's a period in the sense of Kontsevich-Zagier, but it's a period in another sense too. It's a period of that variety. You're doing some integral over the variety. Okay. But now, if we want to understand the geometry of that variety, and in particular, if we're not just sort of getting some coincidentally special piece, but if it's really telling us what's going on overall, then we should also be able to access that by looking over finite fields. So, and in particular, if you're in this mixtate case, what should happen is that these point counts should be a polynomial in P. Okay, that's not obvious a priori, but that's part of what this overall mathematical structure tells you, is that if you get all these shoulds lining up, then that's one of the things that you should get. And then in that case, C2 of P is the quadratic coefficient of this polynomial and is the lowest non-zero coefficient. Because we already said this number is divisible by P squared as long as the graph has at least 3 vertices. Well, lowest potentially non-zero. It could be 0, but the lowest, I don't know. The smaller ones are 0. That's the 2 in C2. So in particular, it would not be dependent on P. So it's just a constant. Okay, but this is all false. So if they're all multiple zeta, it's false that they're all multiple zeta values, right? This is not true. All multiple zeta values is false. But the should be's all still work, right? So there's still these connections, and some of them are really should be connections, because it's of course possible that when you take this Feynman period, you're not seeing the whole geometry of this variety. So it's possible that it's catching something that's missing the general picture. It's catching something special. But broadly speaking, there still seems to be a lot of use in trying to understand this guy in order to understand the Feynman period. So even though it's false, even still, this C2P is an interesting sort of measure of what sort of things should be going on in PG and its geometry. And again, some of you have probably heard a lot more and you know some of the caveats. There are some interesting caveats here, but it's still broadly speaking an interesting thing. Okay, well, I want to do some graph theory. And I told you a whole bunch about symmetries. Why did I tell you a whole bunch about symmetries? Well, if C2 is supposed to tell you something about the period, you know, it better have the, you better understand what's going to go on with these symmetries, these graph symmetries. And sure enough, the C2 invariant either has or is conjectured to have nice properties for all of these things. It should be completion invariant. I'm going to come back to that one. It should be duality invariant. This is proven in the planar case, Dumitru-Doran. And he proves actually more than the planar case and conjectured in general. There should be a twist invariant. That's conjectured. It depends at least on completion. There should be a Fourier split. The 3 join, it doesn't give a product. It just outright gives 0. And that makes sense if you think about what's going on with the transcendental weight. And in fact, the C2 is, it's sort of seeing the transcendental structure in some nice, well, at least it's giving a hint of it. It's giving a view of it. And so you shouldn't be too surprised to have a double triangle invariance, which is actually one of the first things we proved. It's actually easy. I say it's easy because it's my proof. Of course it's easy. And it's conjectured that if 2 graphs have the same C, no, that's the wrong way around. I wrote the converse. That's the false one. Don't read that. Don't read that. Don't read that. What's conjectured is if they have the same period, then they have the same C2. And what I wrote is false. And the converse is definitely false because, for instance, there's all sorts of stuff that gives 0. And interestingly, it gives zero. Zeros are nice. They're weight drop. Anyway, don't read that. That's actually one thing I like about doing these talks with the pen, is that if there's something really stupid on your slide, you can get rid of it. Okay, I wanted to say a few things since I'm trying to talk about the graph theory that underlies these things. I wanted to say a little bit about other graph invariants that have these symmetries, or that have some things related to these symmetries. And the first one was developed by a PhD student of mine. And unfortunately, I'm not going to say much about it because it seems to be completely useless for physics, which is really too bad, because it's got the right symmetries of the period. So you would really think it's got to be telling you something. But we could not figure out what it was telling us. We could prove lots of stuff about it. It's actually much easier to prove stuff about this than it is about C2. So what do? You take a signed incidence matrix. Let's just call that E, with one row removed. So that's the full rank version. So what is that? E is, remember, these are edges and these are vertices, except there's one extra vertex that we've removed. And what do? You orient all the edges, you put a +1 for one end, a -1 for the other end, and zeros everywhere else. And then if you do that, well, you could stack these up to make a square matrix. So for the sort of graphs we've been talking about a lot that are 4 regular but with one vertex removed, if you stack 2 copies of this up, you'll get a square matrix. And then you can take the permanent of that matrix, and then you say, I don't like permanents. They're bad objects from the point of view of linear algebra. But they're not bad objects if you take them modulo 1 more than the number of copies that you've stacked up. So this you want to take mod 3. And for some other one, you might stack it up a different way, and you take it modulo 1 more than the number of copies you've stacked up. And then it becomes a nice linear algebra object, because that when your matrices have this special form and you take the mod that number, then you're actually back to now having an object that is compatible with row reduction, and so is in fact a linear algebraic object instead of just some sort of thing. Okay, but I'm not going to talk about that because it seems to be useless for physics. Eric Hanser made this HEP invariant, and how did you do that? You take only the dominant term in the Kirchhoff polynomial in each sector, right? So it looked like this, and for any given choice of the variables here, there's going to be one monomial that's going to be dominant, and so you just take that. So it turns into, instead it's like the max monomial. This isn't actually notation, but you know what I mean. You take that max monomial. Yeah, we do that guy. Now, this guy is pretty nice, actually. I think it's a really nice invariant, and it also seems to be particularly nice for physics, unlike the permanent, which is not useful as far as we can tell. And it's useful for 2 reasons. So this is all Eric's work. This is not mine in any way. One is that it really looks like it might actually be if and only if. That result that I wrote the wrong way and then I fixed it, but for sure that one's only one way for C2. It really should be if and only if in this case. And also empirically, when scaled, it matches the value of the period very well. And some of you have probably seen this from Eric has given a lot of talks on this. So what is this? This is the HEP, suitably scaled, and this is the period. And all right, look, when you scale them the right way, you get a very nice linear relation. And all right, the right way is a little non-trivial. It's logarithmic on both sides. You have to do a little bit of a loop order scaling, but then you get a nice empirical line. Okay, so I'm not going to say more about that. This conference was called Elliptics and Beyond, and so far I have not said anything about any of that. I've just done a little bit of graph theory. So how do we see the elliptics and beyond showing up in any of this story? So first of all, the C2s, they're numbers, and well, in the 90s, they looked like they might all be multiple zeta, but that turned out not to be true. So what are the ones that aren't? Well, okay, elliptics and beyond. That's good. We're finally getting into the topic of the conference. Okay, but this is in the C2 section, so why am I doing that? Because C2 gives us a good way of seeing actually this side of things. Because what C2 sequences do we see? Well, we see constants, 0 and -1. Okay, those are nice. Those are, the 0 are the weight drop guys. And the -1s, well, do you remember how I said these things that came from double triangle of K5, or that's completed, so double triangle of K4, if you're thinking of the scalar 4-point graphs? Those seem to be the -1s. And that's actually another nice conjecture that is sort of a graph theoretic conjecture, which I really like. There's also ones that are almost constant, like they have a problem at p=2, or you need to put in some roots of unity. Then one of the things that gets certain classes of number theorists exciting is you get the modular forms. So okay, that's sort of, we're getting there, we're getting to elliptic here, right? So here's a table of some of the ones that show up. Now, it's a little bit, what the heck is this table showing? It's showing weight and level. Now notice a few of these have been proved, but this is mostly empirical. So a few proven, most are empirical observations. Okay, what do I mean by an empirical observation in this case? I mean, you calculate out the coefficients for C2 a certain ways. You calculate out the coefficients of the Q series of the modular form. Well, you don't, you look it up in a table where somebody else computed it out, and you say, aha, those look the same. Now, and here are the weight and level then of the observed modular forms that you seem to see. Now, this is not just these graphs. We did a lot of these 4 regular, so 5-4 graphs. If you only do the 5-4 graphs, some of this goes away. So these ones in particular, they are only showing up, so far anyway, if you are allowed to go beyond the 4 regular situation. So that's kind of interesting, actually. And this is one of the things, and again, you may have heard other people say this, because this is not my observation, but I think it is one of the interesting observations in this area, is that, okay, what is this? This is the elliptic curve case, right? Weight 2. Okay, but that doesn't show up at all if you stick to 4 regular. So this column here, I've kind of marked it over, but remember, those ones were all ones that were not, that required vertices that were degree more than 4. So sticking with vertex degree less than or equal to 4, you get no elliptic curves. And that's interesting. I hope you find that. I think that's very interesting. And you can ask some people who are not me, and I can tell you a few things about that, but there's not really a good understanding of that. Okay, you get various things. Okay. And now that's not everything, because there's also plenty of beyond. There are plenty of unknown sequences, and so if you're really bored, here's a sequence for you. And you can find more of these. There's a paper of Brown and Schnetz about modular forms in QFT. And again, it's a bit older now. This table is actually slightly updated. This table is actually from something I did with Oliver and 2 undergrads, where we did some updated computations. Okay, I have just a couple of minutes left, and I want to say something that's actually my own work. I mean, I have figured in a small way, and some of these other things, actually double triangle is substantially my work too, but here's something new that's my own work, along with one of my master's students, Simone Hu. And this is our theorem. I think this is, and that is that the completion conjecture holds for the prime p = 2. Okay, and here it is written for the mathematicians, or if you forgot what all this was about, we have a 4 regular graph, K, and 2 vertices. Then we've removed those 2 vertices. Now we've got 2 graphs that are the kind we liked the most, which corresponded to the 4.54 graphs. And we calculate their C2 at 2, and you get the same thing. You get the same residue. Okay. Now, if you heard, a few people will have heard me give talks a year or 2 ago, 3 now maybe, a little while ago, where I could do this in the case where K had an odd number of vertices. And I told everybody at the time that that was clearly an artificial requirement. It was a requirement for the way I was proving it. I did half of this, basically. But then I got a smart master student, and she did the other half. So I'm very pleased about that. because now we can at least say completion holds when p equals 2. Of course, we're thinking about the other values of p. That's a nice result, because I think this completion conjecture really is one of the big open conjectures still in this world. And it's gone to be the point that I think some people are starting to doubt that it's true, just because, you know, smart people have thought about it. Well, Francis, certainly. He's a smart person for sure. I don't know if I should say much about the proof. I think I won't go on to another page. That's the thing to do. Let's just say a little bit about the proof here. It's a different talk, really. It's a nice talk. It's actually totally elementary. I could explain this to all of you. You don't need to know anything sophisticated. It's a beautiful, beautiful proof. But it takes more than 3 minutes. But what is the idea? The idea is you reduce calculating C2 to counting, and now in the p equals 2 case, certain edge bipartitions of the graph. With certain properties. And did I mention I'm from a combinatorics department? I mean, counting edge bipartitions of graphs. I mean, come on, that's like classical, beautiful, just pure enumeration, and it's graph theoretic too. It's really, really nice stuff. Okay, but all right, you can't, okay, and what do we need? We need to count the modulo too. So what do we need to know? To know that the sets for the two sides have the same parity of the counts. Okay, how can I show that two counts have the same parity? Well, I got to pair them up basically, and it doesn't matter if I pair them up within one of the sets or if I pair them up between the two sets. So I might as well just toss everything into one big set, all of the edge bipartitions for both graphs, toss them all together, and then I want some involution on that set, and that'll tell me, okay, it's even. If I, assuming, you know, I fixed point free involution, and then I'm done. So find a fixed point free involution. I mean, this is absolutely beautiful classic enumeration stuff. And that's exactly what we do. And at first I couldn't. And that's why I could only do one parity of the number of vertices. So I had to do something more complicated. And once again, I used some really beautiful things that you teach in your second year classes. At least I teach in my second year classes, which is just fun. But Simone finished it. She managed to complete it in the other case. So I did this for some, but I couldn't finish it. Simone finished it. And now I think some people feel that we're never going to get it for higher p, because in the case of general p, they're not bipartitions anymore. They're two p-1 partitions. Partitions into two p-1 parts. And they're not of the edges, they're of p-1 copies of the edges. And you know, that's more annoying. Definitely more annoying. But at some level, that's my area of expertise. My area of expertise is annoying combinatorial things. Because if you look at them long enough, they turn into beautiful combinatorial things. And then if you're lucky, they also help you with your quantum field theory. And that's what I like to do. And here are some examples here at the end of some ways that I've done it, and earlier some examples where other people have been doing that. And I'll stop there.
Thank you for the talk. Let's take a moment to unmute and give a round of applause. I believe David is the first question.
Thank you, Karen. At least one member of your audience was deeply fascinated. I want to make a very modern correction to something that you said. I believe that Eric's conjecture that the het bound is faithful has been disproven by Oliver Schnetz for 3 regular graphs for phi cube theory in 6 dimensions.
Okay. So is it still a live conjecture in the in the 4 regular case, or does he
Yes,
not?
I believe so, but
Okay.
that's information. And I then want to make that's a bang up to date comment, you know, further than your knowledge. But I also want to thank you for the historical perspective, but to say that you seriously underestimate the length of my engagement in this subject. In 1985, I wrote a paper on massless scalar Feynman diagrams, 5 loops and beyond. I did everything at 5 loops, and I stuck at 6 because I had an irreducible double sum. This is the origin of multiple zeta values. But at that time, in 1985, the referee of the paper said, there are no scalar particles in the world. He hadn't heard of the Higgs boson. There's no phi to the 4th interaction. He didn't know about Higgs work. And no one will ever need to do any calculation to 5 loops in quantum field theory. And we have the 5-loop QC beta function. So if there's anyone around here about the age of 35 who's getting referee reports like that, just wait until you're past 70 and maybe the review of your work will be more favorable.
David, am I allowed to include this thing about the disproved more generally by Schnetz? Because if these slides go up with the annotations, is that okay, or is that still sort of? Okay.
Oliver is attending, and Oliver is not attending, but Eric is. Eric knows about this. Discuss it with him.
Okay. I guess I won't upload my slides right away.
Okay, that should be fine. Our next question is from Pranav Sisla,
Yeah.
whose name I probably didn't pronounce correctly.
Yeah, you pronounced it properly. Thank you. I had a doubt that is there any type of contradiction between Feynman's path integral and the relativity? Because as we know, if it takes like infinite velocity or infinite amount of velocity to go from a finite position to infinite position, which actually in the theory of relativity, it says that you cannot cross the speed of light. So I saw this somewhere in the internet a few days back. I wanted to know if there is some kind of contradiction or not. I don't know if the question is valid or not, but I checked it in the internet. I got it in the internet.
The question isn't really applicable to this conference, but Karen, if you want to say something, sorry.
No, I don't think I was going to have anything to say other than that. Yeah, these calculations are not speaking to that in any direct way. We're looking at it of an individual.
I know. I know. I just wanted to clarify if you knew about it or something. Like I knew that this wasn't related to this, but it was pestering in my mind for a while.
I don't have anything to add to that at the moment.
Okay, thank you.
I can maybe find you some resources later. Let's see. There's no other hands risen right now, but I did have a question about the C2 invariant, or I guess more broadly, whether, since the C2 invariant has got this very nice way to indicate weight drop, to indicate ellipticity, or anything like that, not for Feynman periods, but for more general Feynman integrals, as in if you add kinematics, is there any hope that there's some object that has these properties?
Yeah, I mean, I think there's hope, but I don't have a concrete thing to say right now. I don't know if David has something he would add to that. He might be the one who would have a good concrete idea. The thing is, so here's how you would try to find something like that. You would say, okay, again, you have to put on your algebraic geometry hat for a second. You say, as an algebraic geometer, where is this coming from? And then once you've found where it's coming from as an algebraic geometry, you say, can I access that in some other way that's maybe a discrete way? Because that's part of what C2 is doing, is because it's discrete, it has some advantages for computing, say.
Okay. David, you were trying to say something. Go ahead.
I think what Eric is doing at present is really very important. Karen referred to it in this graph. The Hepburn bounds, which you can, are essentially combinatorial objects, they are rational numbers, that they are wonderfully accurate predictors of the actual values these amazingly complicated integrals, whether they be elliptic, Calabi-Yau, quantum field theory will outgrow any mathematical attempt to contain it. You go to enough loops and you've found some new object down here. But I think what Eric has done here is actually show that there's a combinatoric, a rational, we're plotting immensely difficult to calculate graphs against rational numbers here. I think this is just an extraordinary thing. Now, the person that is most likely to exploit this is Misha Berinsky, who has developed a Monte Carlo algorithm for multi-loop diagrams, and by multi-loop I mean 20-loop diagrams, which are absolutely impossible by sector decomposition, using Eric's HEP bound to determine the Monte Carlo sampling. And he can calculate 20-loop Feynman diagrams to 5 significant figures by sampling only 10 to the 10 points using this. So there's something really, really important going on. It's still at the level of the simple single scale periods that Karen's been talking about. It has prospects, and Mishy's most recent paper shows this applications. But we have something here that's developed just in the last couple of years with these two wonderful young people, Eric Panzer and Misha Berinsky, that can give you 5 significant figures of a 20-loop Feynman diagram in a few minutes. That's big news.
Thank you. It's fascinating. Let's see. I don't see any more hands raised. So in that case, we can thank Karen again, and I'll see you all tomorrow, either tomorrow morning for those who the time zone works out, or otherwise for the talks tomorrow afternoon. Thank you all.